Okay, welcome to the 7th class meeting of the Introduction to DSP. Sorry about my voice. The first announcement is the homework, as usual. And second announcement is about the quiz 1 we are going to take on this Thursday. As I already sent to you short messages to your smartphones, I've changed my mind. So quiz 1 will be close everything quiz. The reason why is that I made up the problems and I asked the LLM, and even I scrambled somehow, believing that LLM cannot recognize the problems, but the solutions were perfect. So what I found is that no longer we can allow LLMs even improving something, solving something type thing, if it is a well-known fact. For example, this DSP material, there are tons of DSP materials. So LLMs have learned all of them. So if I provide you some fundamental questions to solve, then LLM knows how to answer. So I've decided not to allow you to use LLMs, and even no textbook, no computer and everything. Only when you upload your solutions to PLMS, you can use your notebook or some other device. So be prepared to upload your solutions. Got it? And also when you upload, each problem has sub-problems, and maybe your solutions have multiple pages. Please mark carefully which page you capture. Got it? Okay, still here we are, and we are reviewing what we learned in signals and systems about the discrete time signals and systems. So this part, just a second. Yeah. Sorry about that. Sometimes where are we? We are here, right? Yeah. So yeah, this part is mostly covered in any signals and systems. However, from Z transform, some of signals and systems course do not cover. So we are going to cover it. And then we study more serious stuff. As I told you, what is most important in this course is the discrete Fourier transform we haven't yet seen. However, you know what is discrete time Fourier series, and there is a very close relation between DFT and discrete time Fourier series. Anyway, you will see in the quiz. Got it? Anyway, so here goes the review. What was the most important message we learned in the last class meeting? It is this. We want to rewrite our discrete time signal as a linear combination of functions from a basis. And so it's like our signal is going to be rewritten as sum of some basis functions. Got it? And this phi of k of n's, some set, is a basis. Here I say a basis means that there could be many bases. Then which basis is appropriate for our application? It depends. So there are many useful bases used in digital signal processing, not only the Fourier basis. The reason why Fourier basis is so important in signals and systems and introductory DSP is that we are mostly handle discrete time LTI system. And as last time, as we've seen, what happens if we apply a Fourier basis, which means that we apply a discrete time complex sinusoidal signal. then interestingly, output is exactly proportional to our input with the same radiant frequency. But here we have some eigenvalue, which is what? Which is exactly discrete time Fourier transform of the impulse response evaluated at omega 0. This is why we love Fourier basis when we want to design, when we want to analyze a discrete time LTI system. So if some condition is changed, like for example, we want to no longer we want to handle discrete time LTI system, but general discrete time linear system, then what kind of basis do we need to use? Of course, we can still stick to Fourier basis, but sometimes it's very, very inefficient. So people have devised different bases for different applications. So even though this course and signal gen system focus on Fourier basis, never believe that Fourier basis is everything. Fourier basis is very important, but occupies very small world. And many people have discovered some new bases. It turned out to be very, very useful as our technology evolves. For example, there is so-called a Hadamard basis, and that looks okay, interesting, and suddenly it had found a lot of interesting application when our internet is used to transmit a lot of medias. Of course, in the early stage, there were only text, but when you wanted to transmit images, Hadamard basis became very, very important. And people noticed that, and also people evolved that idea to some new idea of wavelet transform, something like that. And the kind of inventor or the best contributor of wavelet transformation, he is kind of renowned and also worshipped as we respect Albert Einstein in physics, something like that. Anyway, you may be a person who invent new bases for some future application. Anyway, so this is the key. Even though I talked a lot, in summary, these lines are the keys you have to have in your brain. Today, we are going to finish this handout by covering many important results, but mostly counterparts of what we learned in signal gen systems for continuous time signals, continuous time Fourier transforms. So you will find very much familiarity. Okay, here first, we want to find when a discrete time signal X is Fourier transformable. So as you remember, Fourier transform of this sequence or discrete time signal is defined as what? The signal and complex exponential sinusoidal signal in a productive over for all n. Here, as you know, e to the j omega n conjugate is same as e to the negative j omega n. That's why you usually remember dt Fourier transform as summation of signal times e to the negative j omega n. And of course, the left-hand side vividly shows this is a function of omega, which is real. And here, as you see that, after you sum up over all n, only variable you have is omega. So actually, for each omega in the real set, you need to evaluate this infinite sum. And last time, I kind of puzzled you by talking about rearrangement of the terms in an infinite sum. And I just gave you some interesting results, like if you have, even though the sum looks infinite sum. If you have finite number of non-zero terms, then any arrangement gives you the same answer. However, if you have countably infinite number of terms, non-zero terms, then you may have a serious problem in convergence, which means that you may not define this infinite sum properly. So in the same line of idea, this right-hand side may not converge to a single limit. That is the question of when x of n have DTFT. Got it? Or when does this DTFT exist? Got it? So this is related to the existence. And our textbook gives you, and textbook and handout gives you a kind of white lie, because it's actually the existence of DTFT is not simply taught in undergraduate electrical engineering courses, because it involves basic mathematical analysis about sequences of something. And some of you may have or will be taking mathematical analysis offered in the Department of Mathematics, and we'll find that the course is all about sequences. And you may say that, hey, in high school, the sequences occupied a very small number of pages in our entire curriculum. The reason why is that it's too complicated. It's not easy to be taught to everybody. But when I became a PhD and did some research, what I have found is that what distinguishes high school math and college level or postgraduate level, which means that PhD or master's level mathematics in engineering or science, is the knowledge about these sequences. This is very important. Anyway, I will give you simple ideas. So here, first thing, so when does this infinite sum converges? And can we find necessary and sufficient condition? What does that mean? Suppose we have the set of all discrete time sequences. Then can we find a subset? Can we describe a subset and say that, okay, if and only if necessary and sufficient sequence is a member of this subset, then its Fourier transform, discrete time Fourier transform exists. Otherwise, it does not exist. Can we find such description, necessary and sufficient condition? And interestingly, we can. And that is absolutely summability. So if our discrete time sequence is absolutely summable, what does that mean? After taking the absolute value, and if this infinite sum, now this is an infinite sum of what kind of terms? Non-negative terms. So it became very good, right? And if this is finite, then its DTFT exists. And here we have seemingly obvious inequalities, but actually if you think over, it is kind of preposterous. So it's like, okay, if it converges, this is true, then what? Something like that. So don't be too bothered with these inequalities. And actually, about this condition, you just need to, very good, memorize. No one will ask you to prove. And if you want to prove it, ask LLMs, and I guarantee that definitely LLMs will not give you correct answers, because it's not that popular thing. Got it? Anyway, the problem is that the reason why I said the textbook gives you a white lie is that we are not just interested in finding a DTFT of a signal. For example, if we wanted to rewrite our discrete time signal using a weighted sum of complex sinusoidal signals, then not only this coefficient need to be exist, but also this integral also need to exist. Got it? So it's not guaranteed that even though your DTFT exists, it's not guaranteed that the right-hand side always exists, which means converges to the original discrete time signal. So the theory is not that simple. But we just say that, okay, it's good, it's okay, something like that. Okay. So when I was an undergraduate student, I studied very hard on signal gen systems, but whenever I confront the convergence issue, it's like I was walking in a fog. And I blamed myself, saying that I'm stupid, I just cannot understand. But when I finished PhD, I eventually found out that almost no professor in electrical engineering really understands and proves that when he was even he turns 55 years old. Okay, probably he once proved that when he was very young, taking the math courses. But yeah, I cannot remember the proof. Got it? But anyway, so not good. The problem is that suppose x of n, some certain x tilde of n sequence is absolutely summable. But my question is that, can we rewrite x tilde as a linear combination of complex sinusoidal signals by using its Fourier transform? The answer is no, unfortunately. So what people have found is this. They define another one, square summability. What does that mean by square summability? Now you take the absolute value squared and sum up. And if this is finite, then you have something good. Unfortunately, as I have drawn here, some signals are absolutely summable and square summable, but some important signals are not. For example, just complex sinusoidal signal. Is it absolutely summable? No, because each term is 1, and if you sum up, it goes to infinity. Something like that. And of course, it's not square summable. But that's very important, something like that. The reason why we consider this one is that whenever you have some sequence thing, and if you have squared sum, then it's very good. Sometimes you can easily prove some important results. Probably that is one of the reasons why in statistics and probability, we love variance and standard deviation instead of absolute error, mean over absolute error, something like that. Anyway, so what's good? If it's square summable, then this infinite sum actually is replaced and redefined. And we can show that it always converges. Of course, even though I said we can show, but we cannot show. Otherwise, we take analysis course and we take the limit. And at that time, this is actually not Fourier transform. This is Fourier-Plancherel transform. And if you talk about Fourier-Plancherel transform, some textbook just says this is Fourier transform, but actually they are different. In Fourier transform, what you need is the summability of these terms after any rearrangement. However, in Fourier-Plancherel transform, there is no rearrangement. You have this one. So you consider finite term summation and consider its limit. Some of you who took signal gen systems from me will be very familiar with this argument. Anyway, so here our textbook says that what's good is that DTFT and its truncated version. See that? Again, when you define, after you take this limit, you have finite terms from capital M to M, and you let limit to infinity after you obtain something easily computable and proven to be finite. Got it? Anyway, it's very confusing, I understand, but you just remember this one. Okay, if we have something involving countably infinite terms, I need to be careful. So what I need to is to memorize some results from mathematics very, very precisely. I don't need to prove that, but I need to be very careful when I talk about something. Got it? So that is my message. Anyway, here goes low-pass filter example. And here is an ideal low-pass filter with cutoff frequency omega sub c. And now we consider impulse response. And it's not that difficult to show that this ideal low-pass filter has impulse response sinc function. This is called a sinc function, as you remember. And now let's consider time windowing or truncating in the time domain, and then consider DTFT. So when we compute DTFT, we multiply the signal with e to the negative j omega n and sum up for all n. But now here, since we have truncated, actually it turns out to be a finite sum with some 2 capital M times 2 capital M plus 1 terms. Now let's consider this DTFT. What would be the difference between these two? So these two are Fourier transform pairs, and what I'm asking is that what is the Fourier transform pair with this one? And if we plot each discrete time signal for different m's, we have these figures. And you remember from signal gen systems, this is a figure to explain Gibbs phenomenon. By the way, Gibbs is the person's name, so Gibbs phenomenon is the correct one, or the Gibbs phenomenon. Got it? Anyway, what is Gibbs phenomenon? Gibbs phenomenon is that if we have truncated the infinite sum to a finite sum, then we have smaller and smaller error energy if we increase the number of terms. However, the largest deviation from the target signal from that approximation does not diminish. So this peak value converges to something. I remember 1.07, something like that. Ready? So what happens? We have some error whenever we truncate, but error's energy reduces. And you may say, why energy? This gives you some idea. As you remember in signal gen systems, energy of a signal can be computed in the time domain as a square sum of square integral, depending on whether this is continuous time or discrete time signal. And in the frequency domain, you had what? The Parseval's relation. And Parseval's relation was related to what? Integration of the Fourier transform. Not just taking the Fourier transform, taking the magnitude square of it. And this is the magnitude square of difference, right? So the energy goes to 0. Error and the energy of the error signal goes to 0. And what is that important? What is the meaning of that one? in electrical engineering, even though we use mathematical models, what makes our electrical system to control robotic arm or some autonomous vehicle or even communication device is energy. So some energy turned into a special waveform propagates through the circuit or air, and then it reacts, it activates some part. So energy is the key. So if our approximation has almost no error energy, then we are satisfied as an engineer. Because that small difference will not make practically huge difference because energy is too small. Got it? Anyway, so, and this is another one. There are, as I told you, sequences or discrete time signals, neither absolutely summable or square summable. And as I told you, complex sinusoidal signal. So this is a special complex sinusoidal signal with omega equals what? Omega equals what? Omega equals 0 or 2 pi or any integer multiple of 2 pi, right? Then we have or 1. Now, what is the DTFT of this one? Actually, it's very complicated to derive, but we can inverse transform that one and say that, hey, I cannot prove from this one to that one, but from that one to this one is okay, so we are done. That is the kind of hand waving or white lie used in non-math mathematics department courses talking about this infinite sums. But anyway, so use the synthesis equation and you will find that this will give you that one. Got it? Anyway, what is important is that, so this is constant. So in our sense, there is DC term, so zero frequency term. So definitely there is a delta function. And that's not everything because by definition, DTFT over sequence is always periodic with period 2 pi. So you have another, and actually countably infinite number of delta functions, 2 pi separated apart to the neighboring delta functions. And now, so this is the basic one, and this is the second one. So now let's consider some non-zero or non-integer multiple of 2 pi, and what will happen? And the answer is very simple. You shift this figure to the right-hand side. So here, omega 0. Here, omega 0 plus 2 pi, dot, dot, dot. And negative 2 pi, dot, dot. Got it? So these are stories. And another one, finally, what if we have some signal that is a linear combination of complex sinusoidal signals? Then each this signal has some form like that. So you take summation, AK, summation and AK, and then here goes the infinite sum, here goes 2 pi, here goes delta function with now offset omega sub k. So that's the story. Okay, here goes so-called tons of tabulated results you need to remember, and it reminds you the undergraduate signals and systems. And let me directly go to the table. So here, suppose you have a discrete time sequence, discrete time signal x of n that has discrete time Fourier transform, precisely speaking, Fourier-Plancherel transform, capital X of e to the j omega. Now, usually we say they are Fourier transform pairs, and here goes questions, 13 questions, and each question says, hey, okay, you have X of n. Now I have y of n, that is the complex conjugate of this signal. Now, the question is, what is capital Y of e to the j omega? Which means that what is the DTFT of y? And in the first line is about when y is the conjugate of x. In the second line, when y is the conjugate and time reversed version of x. Third one is the real part of x. Fourth one is the imaginary part of x times j. Be careful. It also was very confusing when I was an undergraduate student. Suppose you have a complex scalar z that has a plus jb, where j is the square root of -1. Then what is the real part? Everyone gets it correct. What is the imaginary part? That is not jb. It's b. Got it? So actually, this is what? This is that part, simply say. And so given this relation, how can you find the Fourier transform of j times the imaginary part of x? And fifth one is that what is the so-called even part of x? What is the DTFT of the odd part of n? But precisely speaking, even though here it says even odd, actually this is conjugate symmetrical part and conjugate anti-symmetrical part, or conjugate asymmetric part. So here you have a conjugate symmetric part, conjugate anti-symmetric part, something like that. So this is the basic set. And second set is this one. Now, we've consider a special case when the signal is real valued. And you may say that, hey, why real valued signal is so important? Because complex signal includes all the real valued signals. You are right. However, for example, consider a matrix that contains all the elements from 0 to 1, and saying 1 is black and 0 is white, or vice versa. And that is so-called gray-scaled image. And in that case, the number is intensity at each pixel, and it's real valued. And of course, still you can do some kind of two-dimensional Fourier transform. For example, suppose your gray-scale picture has 600 rows and 400 columns. What you do is that you multiply 600 by 600 DFT matrix in the front, and 400 by 400 DFT matrix Hermitian transposed afterwards, and you compute, and you eventually get 600 by 400 complex valued signal matrix that contains all the information, because this transform is invertible. The problem is that before you had gray-scaled real valued one, so if you want to store it, you need not many bits. For example, if you assign 16 bits. Now, after you have complex ones. So you have what? Many bits you require. And also, it's not easy to directly see and perceive complex signals. So people don't use that. But as you see here, people use real valued Fourier basis, which is more familiar with us, cosines and sines. They are all real valued. So for real valued signals, we can use complex sinusoidal signals, but sometimes, not every time, but sometimes we prefer using cosines and sines. And you will see, because I am going to give you someday in this semester as a MATLAB homework, you will perform so-called discrete cosine transform to an image matrix. And you will see at that time. Got it? Because I'm going to ask you to multiply DFT matrices to get some result, and also you perform discrete cosine transform to that real valued image. Anyway, so this is what you need to remember. Suppose x is general complex valued discrete time signal having its Fourier transform denoted by capital X. So this is given. Okay. So given the first line, show 1, 2, 3. Got it? So if this is true, what is the DTFT of time reversed version, conjugate version, and time reversed conjugate version? And this is what I exactly told you. Now here, special case. So X is real. What does that mean? Real means signal and its conjugate is the same for all n. What does that mean? This one and that one are same signals. So this one and that one must be same signals. Got it? So using this property, we have these relations. Got it? So you do it yourself. What you need to remember is that if signal is real, in the frequency domain is conjugate symmetric. That is very, very important property. Got it? Okay. And real part of the Fourier transform is even, and imaginary part of the Fourier transform is odd. Magnitude of Fourier transform is even. Phase angle of the Fourier transform is odd. Same as in continuous time Fourier transform. And the last set is these two. And here, even part of xn and odd part of xn. And you may say that, hey, what's the difference between these two? Assuming they are real, okay? So here xn is real. Anyway, so here goes some simplified notations, like Fourier transform is denoted by this calligraphic letter F operator notation. And inverse Fourier transform has F inverse. And sometimes this, as I have already shown you, you have both side arrow and has the F in between the heads of the arrow. In section 2.9, we have some important Fourier transform theorems. And you may say that, hey, when do we have the end? It's kind of endless, but we are going to end. So Fourier transform has property. First one is that suppose X has Fourier transform capital X and Y has Fourier transform capital Y. Then first question is, what is the linear combinations Fourier transform? And the answer is that linear combinations of Fourier transforms. Whenever you have such relation, never to try to remember the figure or kind of try to memorize this as some picture. You always try to verbalize the result, as I just told you. Linear combinations Fourier transform is the, Fourier transform of linear combination is the linear combination of Fourier transforms. In this way, you really understand, and whenever you want to use your tool, the tool pops up. Hey, master, here is your tool, something like that. Otherwise, even though you have millions of useful tools in your toolbox as an engineer, you will never be able to use anything. Got it? And second one is that the DTFT of the delayed version is what? DTFT times e to the negative linear phase shift. Got it? And here, what is that? DTFT of modulated signal. So this is complex sinusoidal signal that is called carrier. And carrier is modulated by your original signal. And what happens? It translates in the frequency domain. So as some of you have taken in Introduction to Communication Systems, it shifts the Fourier transform to an upper frequency band. with center omega 0. Now, we've already done this one, and that one is n times x of n. And it's kind of interesting. And this has derivative of the Fourier transform. Got it? You need to remember that one. Sometimes it's very useful to know that one. And here goes the important property, not just in math, but in systems theory. Suppose you have a DTLTI system with input X, impulse response H, and output Y, then we know already in the time domain, the output is convolution sum of these two discrete time signals in any order because it's commutative. Now, what are the relations among the Fourier transforms of these three? And it's very interesting that convolution in time domain is product in frequency domain. As I just told you, product in the frequency domain, convolution sum in time domain. In that way, you verbalize your result and always remember. What about this one? This is the product in time domain. And you see kind of convolution in frequency domain, but careful, circular convolution. And one of the reasons why is that DTFT is periodic signal. So if you just convolve two periodic signals, it never converges in most of the cases. And this finite integral integration interval guarantees, not guarantees, but enables you to have finite integral. But anyway, try to prove that one. And here are Parseval's theorem. Actually, this is called Fourier-Plancherel theorem. And this is a special case when x equals y. So here, if you replace y conjugate with x conjugate, then you have x of n absolute value squared. And here, you already know that this becomes x conjugate. And if you multiply something with its conjugate, then you have absolute value squared. Got it? So this needs to be interpreted as inner product in the time domain, and that is inner product in the frequency domain. And also, this can be interpreted as the energy of the signal, and this is also in the energy of the signal. Okay? So energy of a discrete time signal can be computed in the time domain and the frequency domain by using Parseval's relation or theorem. There are some important signals that have important form of Fourier transforms. So delta of n, which is 0, 0, 0, 1, and 0, 0, 0. And what would be the frequency domain weighting of this signal? It has all 1. Here, this is not 1, all 1 for all omega. So it's a constant function with constant unity. And now what happens if you delay it? You've already seen that. If you have Fourier transform of some signal, and the delayed version of that signal is original Fourier transform times e to the linear phase shift. So this is 1, you have 1 times the linear phase shift. Got it? And now, what about all 1 signal? All 1 signal is constant, and we, as an electrical engineer, we call it a direct current signal and low frequency modulation, which means that after Fourier transform, it must have what? The delta function at omega equals 0. And at the same time, since this is the DT Fourier transform, we have delta functions at every 2 pi. Now, here goes some interesting things. So first, you have a to the n u of n. U of n is unit step, and which makes the all negative time you have 0 values, and suddenly you have 1. Now you have exponential signal. So it's kind of truncated exponential signal. Now, what is the DTFT of it? You may say that, hey, this is not that interesting and do I need to memorize? Actually, this may look ugly, but this has a very good friend, or it transforms in Z domain. So when you learn G transform, you will really appreciate. So I will talk about it more after we cover the next handout where we review Z transform or we study Z transform. Now, 4 and 5 are closely related. One reason is that as an engineer, we know that, hey, even though it says A's absolute value is less than 1, what if A is very close to 1? And if we just truncate, then 1 to the n is approximately the same as 0.99999 to the n in our practical case. So you may just let A equals 1, and it seems this is okay. But suddenly, we have something strange. Okay? And this bothers us a lot, actually. And I was once asked why suddenly we have that term. And let me just tell you. So this is your van, right? And what you need to do is that you rewrite this one as some signal like this. So you have some constant signal with height 1/2 and some signal as height 1/2 and negative 1/2. And then this will give you that one. Got it? That's the idea. So whenever you have DC term, you know that you have countably infinite number of delta functions. So by rewriting your n in that way, you suddenly have constant function that gives you this term. That is another white lie. It's not easy to handle generalized functions such as delta functions. So what we can just do in electrical engineering is that, hey, accept this, because does it make sense? Something like that. Got it? And also we have another version. So here you have that signal, and you have n plus 1. And you may say that, hey, I just have seen n times some signal. Why suddenly n plus 1? And this is just for beauty. And it's related to differentiating that one. Got it? So it's like what you can do is that you rewrite that one by expanding to 2 terms, and you use Fourier transforms each one, and you get the result. And about that one, you can use something similar. Okay, so this part is skipped. Yeah, this is so complicated. And here goes the time domain sinc function we've already seen. And here goes the impulse response of the moving average. You've seen something similar, so-called Dirichlet kernel. And as you've seen in the homework, Dirichlet kernel is very beautifully defined so that it's kind of, how to say that? The signal itself is real valued. However, that only holds when we have kind of symmetry in defining the Dirichlet kernel. But the problem is that when we Fourier transform these simple moving averages, then we have this e to the negative j omega capital M over t term, or 2 term. One of the way to remove that one when M is even is that you shift it. So that if you have non-causal signal that has capital M over 2 past and future values and M over 2 past values and current value. In that case, you have symmetry. So recall the Dirichlet-Kernel derivation. Got it? And this is the special case of modulation. And this is what? Real part of that. Okay. So it's not that difficult. Okay. And here goes applications. Let me skip. But this I cannot skip. So you may say that, well, there are many DT signals and I've learned the DTFT. What's the use of it? And as I told you, some of the high school math problems related to sequences can be very, very easily solved by using Z transform. However, as you will see in probably this Thursday or next week, Z transform can be viewed as a special case of DT Fourier transform, or DT Fourier transform can be viewed as a special case of Z transform, which means that as you've done in your homework, where you didn't prove the general term form of Fibonacci sequence, you've plotted and have seen that, ooh, they are the same. Some of you already were given that general term formula for Fibonacci sequence when you were a high school student, but some of you have seen it for the first time, right? And to derive that result, you need Z transform, or you can apply DT Fourier transform. So even though here you have a different linear constant coefficient difference equation, if you want, you already have your solution, right? You remember what is the difference equation to generate Fibonacci sequence. And as this shows, you apply discrete time Fourier transform and try to do something, okay? Where if I give you some hint, not just this one, you will have some quadratic equation of e to the negative j omega, which means that not just x squared plus 2x plus 3 type thing, you have e to the negative j omega squared plus 2 e to the negative j omega plus 3 type of quadratic function of e to the negative j omega. And finding the root of it, you will surprisingly find that general form. So try that. Got it? It will not appear, not yet, in this quiz, because we haven't yet studied Z transform, but it will be very interesting. Got it? So as you see here, see that this is a kind of recursion formula to generate the sequence Y, given some X. And given x of n equals delta of n, we may find h of n, the impulse response, by just substituting. And you may say that, what's the use of it? But suppose you have different input and want to compute. Interesting thing is, sometimes you have two terms with something familiar. U of n times exponential function. U of n times some exponential function of n, scaled version. And your general term for the Fibonacci sequence had something similar, right? If you carefully write your answer by using U of n, you had two terms, and each term had some rational scaled to 2 plus 1 over 2 something raised to the power of n, u of n, minus something raised to the power of n, u of n, something like that. Got it? So this type of solution occurs again and again and again and again. I know you are busy and you will be obsessed by the quiz 1 on this Thursday, but what about trying to somewhat 선행학습 to find your own derivation of that formula. Got it? Okay, so we are almost done. Here goes the section 2.10. And as I told you, I will not talk about random processes in this undergraduate DSP course, but I have to emphasize this one. Some universities, when I was an undergraduate student, we had signal-gen systems, covered almost everything in the signal-gen system textbook. So I was taught Z-transform, linear constant coefficient difference equation, DTFT, everything, even control, some stabilization, everything. And we were taught DSP, automatic control. And we found that, hey, we learned this one in signal. Of course, that does not mean we fully understand. So we have found that the curriculum have overlapping courses. And it looked somewhat time wasting. But later, I and my friend found that it was a wonderful curriculum. Let me ask you, many of you have some feeling like this. Hey, it seems that I have drunken alcoholic beverages too much. It seems I got stupid after entering the university. When I was a high school student, middle school student, if I learned, for example, new math, I knew that for 6-7 years and still I just memorized everything. It seems something's wrong with this water in Pohang. No, okay? You remember that because you studied that again and again and again and again and again. Got it? However, many students, after taking signal-gen systems, they never take DSP, they never take random processes course and something like that. They just don't remember Fourier transform. And if you talk about Z transform and your friends say, what transform? Something like that. Why? Because they or your friends studied for only 3.5 months. Because our single semester lasts for 3.5 months. And you believe that after 3.5 months, you still remember everything? No. So it's impossible to fully understand material. Of course, we professors push you a lot during the course. And this overlapping curriculum kind of allows you to repeat the material and deepen your understanding. The pity thing in South Korea, Republic of Korea, is that our government, especially Department of Education, allowed university professors to teach less and less credit of courses, and students to take less and less credit hours to graduate. Hey, everybody's happy. What happens to the student? When I was an undergraduate student, the graduation requirement was 140 credits, and our Gyeongbuk National University had around 190 credit hours to graduate. It's almost impossible to graduate in 4 years, but mostly they graduate. There were a lot of overlapping, but that made the universities, Gyeongbuk National University curriculum, very strong, and the graduates were very well educated and did a lot of contribution to our Korean industry and academia. When I graduated, I got 149 credit hours, so 3 more courses. And now you just take around 120 something or 32 or something. That's not good. The problem is that professors now say that, hey, let's remove all the overlaps. Why we have overlapping curriculum? So let's remove DSP. Everything can be covered in signal systems. The problem is that most of professors do not cover all the material in signal systems. Some professors just talk about continuous time Fourier transform, done. Even no Laplace transform, and saying, hey, Laplace transform is covered in circuits theory. And professor in circuit theory says that, hey, Laplace transform must be covered in signal system. So never believe professors. If they say that, it's okay to not to learn something. Never believe, even if I say something, okay? For example, hey, you can just happy with white lie about convergence of terms. It's not okay, actually, if you really want to do some research in that area. Anyway, so here, our textbook, actually, as you find, our textbook talks about random signal processing, spending around 1/3 of the textbook. And let me skip that one. There are two reasons. When I was an undergraduate student, we didn't cover that, okay? Because there were other too much things to cover in this course. And also, that was too specific, we believed. And that part was moved to graduate curriculum. So it's like when I was taught in random variables and processes, probability and random processes, and graduated, hey, when do we use that one? Because we never used that. Now the story is totally different. Many of the universities and almost every department has their own introduction to machine learning and artificial intelligence. And what is the mathematical foundation? And you may say that optimization. No, it's probability theory. So probably your juniors will have different curriculum. We are going to discuss tomorrow in our faculty meeting. So we are going to move down the random variables and processes, emphasizing probabilistic or statistical inference and optimal decision. So that after you take that course, you may better understand what we want to do with our neural nets, what we want to do our agent in reinforcement learning, something like that. Anyway, so even though I do not talk much about random signals and processes in this DSP course, I'm sorry, because we have too much other thing to cover after this redundant review. So let me just briefly sketch something like this. So here, x of n is no longer a deterministic signal. It's a random process. As we learned in 전자수학 A, and some of professors do not cover that part. And this is this is deterministic signals autocorrelation. And you can define random processes autocorrelation by taking the expectation. So what you need to remember is that a deterministic signal is a special case of random signal where you don't need expectation. So general form of autocorrelation is that you have expectation. Cross correlation defined in the same way. Pseudo noise sequence is a computational method to generate random, pure mathematically random-like sequence, but it's deterministic. And actually, it's very, very useful in secure communication, such as spread spectrum signal, to have the property of low probability of detection, 저비탐 성능, something like that. And they have devised many pseudo noise sequences, not only to be used in radar and communications, but also to drive our generative models in machine learning and artificial intelligence. Probably in your random processes course, if you have taken that 전자수학 A, you've seen some part like this. you have a uniform random number generator. By using that, and you put some mapping rule, and your input uniform random variable is transformed to another random variable of which distribution has our desirable property. So it's like, suppose you have some uniform random number generator whose PDF is something like this. And here, you have some strange function. Then here you have another random variable x. Anybody remembers this one? X is Gaussian if this function is the inverse of the CDF of standard Gaussian, something like that. And this idea is actually, after many, many, many complications, is used on our generative models. And probably you remember this one. Some website says that, hey, if you upload your picture, we will generate a new picture that looks like painted version, not just picture, painted version, but touch of the painter Gogh, something like that. So starry night type thing. You know that picture, right? How they do that? What they do is that they train their function and have your picture input. And actually, here is a pseudo-random noise generator. And simply speaking, you have, is it CH? I do not remember. A Gogh type picture comes out. Got it? So, as I told you, this understanding of random variables and statistical inference, how to generate a new random variable, is very, very important. Every LLM has that kind of idea. That's why whenever you ask the same question, you have slightly different answer, because the pseudo-random number generators will drive your system with different C's. Got it? Anyway, so designing this random-like sequence is very important. And actually, this is one of the very important area in signal processing, especially with a lot of emphasis in mathematics. For example, in our university, there are some professors in math department. I don't remember, he retired, math professor, and our professor, Yang Young-chul, they generate almost the same paper on the sequences using math tools. Galois field, finite field, something like that. And also, Yonsei University, KAIST, Seoul National University have and had professors who majored in sequences, pseudo-random sequences with amazing autocorrelation property, something like that, to be used in signal processing, communications, radar, etc., etc., etc. Got it? Anyway, so let me just tell you first, processing of random signal is more wide thing because deterministic signal is a special case of random signal. That is first. Second one is that in computer simulations, there is no purely random thing. So we generate pseudo-random signals. Pseudo means 의사, 유사, something like that. But designing such a random number generator is not only important in generating pseudo-random sequence, but also has a lot of important application in signal processing, radar, blah, blah, blah. Got it? And your cell phone, handphone, has also so-called reference signal that is heavily relies on the sequences, carefully designed. This part, let me skip. What else do we have? Yeah. This part, let me also skip that one. Okay. By the way, the example I've given you about our Korean stock market, is it random? It's kind of philosophical question. Random something is purely mathematical model to mathematically handle our real world problem. Okay? There is no pure mathematical random thing except in quantum mechanics or something. Suppose you toss a die. You may say that, hey, it's random, but nah. Ask your mechanical engineering friend, and he will say that, hey, here is a cube that has uniformly distributed material, but with some dent to mark the different numbers. And you throw it, and when you throw it, it will rotate with some angle, with some angular velocity, and will fall down on this surface with elasticity something, and it will roll and blah, blah, blah. Okay? There is nothing random, actually. It's deterministic, even though there are limitations in measuring what is the precise rotation angle or speed, something like that. So we have devised mathematical model of something with uncertainty. Got it? So here goes the keyword. Something with uncertainty cannot be handled easily. We need some new mathematical model. So suppose you invest on Bitcoin. There is uncertainty, right? You don't know what kind of price change you will experience right now in your cell phone, right? What can you do? Nothing? No. We want to do something by mathematically model and try to find out some mathematical way to, for example, grab some coins, money from that variation. It may turn out to be useless, but we use our extreme mathematical techniques to squeeze out money from our randomness, right? Engineering is almost the same thing. We want to do something useful. But just guessing and say, hey, what about doing this, does not give us some systematic result. So we use mathematical model and carefully derive the result that can be agreed by anyone with that level of mathematical skill. And we test it. This is very important. Mathematical model is a model. It has limitations. So we need to test that one. And if the results is desirable, then your model works okay. And you put that model to the extreme thing so that you have, for example, more money from your Bitcoin price change. But in many cases, unfortunately, your interesting result like, okay, I have some buy order here, buy order there with twice the amount of money, and then it goes down and goes up, then I get twice. That usually never work. Why? Because your mathematical model is a model with a lot of flaws. Anyway, so some terminologies like Weiss and stationarity, some of you have heard that terminology in your probability and random processes course, and some of you, others of you didn't. And that depends on who taught that part. And if you need that ideas, probably you'd better take the graduate level probability random process course. And here, this E means expectation. And as I told you, we will not cover that in this DSP course. Anyway, probably some of you were intrigued already, even before taking this course, by investing on Bitcoin or some Korea and US stock market. And also after you have done some homework, probably you are interested in processing some signals with uncertainty, like stock market prices, stock prices. And that would be the good starting point for you to have strong interest in studying random signals and processing. And unfortunately, that is not covered in this course. But most of important basics is going to be covered in this course. Okay, anyway, that's all for the day.